So I claim that the basic log functions are just constant multiples of one another. In particular, ln of x. Let's graph y equals ln of x. It's our classic hook, VA at the y-axis, x equals 0. That should be dashed. Now, let's consider y equals log base 2 of x. I'll just type it out. According to the change of base property, that should be y equals log base 2 of x will be ln of x all over ln of 2. So when we go from y equals ln of x in red here, I'm flashing it, to y equals log base 2 of x in purple, I'm flashing that, we get a vertical stretch from the red graph to the purple graph. Above the x-axis, red goes up to purple. Below the x-axis, red goes down to purple. And why is that? Well, the constant multiplier here is 1 over ln of 2, which is about 1.4. So basically, this thing here is, it can be rewritten as y equals 1 over ln of 2 times ln of x. This constant multiplier here, 1 over ln of 2, which is about 1.4, that's bigger than 1. That leads to a vertical stretch of the original ln of x function. And the graph gets stretched. Okay, now what about over here? Y equals log base 10 of x. Y equals ln of x all over ln of 10. Let's change the color. Let's see here. Okay, let's change it to purple. Okay, so let's go from the red graph to the purple graph. Okay, so we're going from y equals ln of x to y equals log base 10 of x, the common log function. Here we have a vertical shrink. Notice the red graph is going down to the purple graph above the x-axis. The red graph goes up to the purple graph below the x-axis. And why is that? Well, this here can be rewritten as y equals 1 over ln of 10 times ln of x. This constant multiplier, 1 over ln of 10, is about 0.4. Not 1.4, 0.4, which leads to a vertical shrink because this multiplier is between 0 and 1, strictly between 0 and 1. It's about 0.4. So that leads to a vertical shrinking of the red graph to the purple graph. Y is about 0.4 times ln of x. Okay, now let's consider this over here. Y equals log base 2 of x. Let's go back to him. Y equals ln of x all over ln of 2. All right, that was a vertical stretch. And now I'm going to consider y equals log base 1/2 of x. So that's y equals ln of x all over ln of 1/2. Now take a look. I'm going to erase the ln of x guy here. We're going from y equals log base 2 of x in green, flashing, to y equals log base 1/2 of x in black, which is flashing. It appears that these two graphs are reflections of each other about the x-axis. And the reason for that is because, in fact, these two functions are opposites of one another. In particular, I claim that ln of 2 and ln of 1/2, these divisors, are opposites of one another. And therefore, 1 over ln of 2 is the opposite of 1 over ln of 1/2. And here's why. ln of 1/2 is equal to ln of 1 minus ln of 2. That's the quotient rule. The log of a quotient equals the difference of logs. But ln of 1 is what? 0, which we can ignore as a term. So look at this. ln of 1/2 is the opposite of ln of 2. Therefore, 1 over ln of 1/2, the multiplier here, is the opposite of 1 over ln of 2, the multiplier here, which is why these two functions are opposites of one another. So if your base is something like 1/2 or 1/3 or 0.1, then the graph looks more like this. It's actually decreasing. But when we think about logarithmic functions, we normally think of functions like log base 2 of x or log base 10 of x, where the base is greater than 1. And we have an increasing but concave down graph like this. And once again, in computer science, we tend to prefer growth in terms of time or memory requirements that's logarithmic as opposed to exponential. Here's y equals 2 to the x. These are inverses, remember.